Hey everyone, and welcome to This Explainer. Today, we're putting on our senior architect hats to tackle one of the most critical and honestly daunting engineering challenges out there, migrating a legacy system. We are going to dive deep into the mechanics of transitioning from a tightly bound, fragile monolith to a highly scalable, resilient microservices architecture. Here is our roadmap for today. We'll hit the monolith breaking point, the strangler fig strategy, hexagonal architecture principles, ports, adapters, and boundaries, and finally, distributed data and sagas. Let's get right into it. So let me ask you, is tight coupling just absolutely killing your deployment speed? I mean, we've all been in the trenches, right? Watching a pristine code base slowly morph into that dreaded big ball of mud. You know the exact feeling, when one minor tweak in the UI somehow brings the entire payment processing system crashing down at 2 a.m. Section 1. The monolith breaking point, understanding the limits of legacy architecture. Look, monoliths are brilliant for getting a product off the ground quickly, no doubt. But at scale, they really force your hand. You have to scale the entire application, deployment risk goes through the roof, and updates get incredibly complex. On the flip side, microservice autonomy gives us independent scaling, strict fault isolation, and much faster CI/CD pipelines. Imagine a single reporting tool gets a massive traffic spike. With a monolith, you're forced to scale the whole system and just burn through massive computing resources. Not ideal. Moving to Section 2, the strangler fig strategy, evolving without downtime. As software design expert Martin Fowler put it, almost all the successful microservice stories have started with a monolith that got too big and was broken up. It's a hard truth, but as engineering leads, we know the best migrations don't start from scratch. They strategically decompose what's already running and generating revenue. Which brings us to the strangler fig strategy. Instead of a massive, super risky rewrite, you gradually replace existing monolithic functionalities with new, independent services. Think of the actual biological strangler fig tree. You build the new, modular architecture safely around the old one. You slowly choke out legacy components one by one, allowing the old and new to coexist securely without ever incurring system downtime. Now, before you go eagerly writing a bunch of new microservices, you've got to define the bounded context and logical domain partitions of your existing monolith. Functions like product purchasing, fulfillment, and inventory management should be logically grouped in your application code way before they ever physically leave the shared database. This is a vital early step to prevent a fragmented, distributed mess down the line. When it's actually time to extract, the sequence is literally everything for risk mitigation. First up, extract a single vertical business capability. Next, split the service behavior into a totally separate module within the code. And then, only after that, do you separate the data tables, making sure to retain a single write copy. By making that logical separation in the existing monolith first, you're safely decoupling the logic before making that permanent split in the database. All right, Section 3, Hexagonal architecture principles. Defining the core. To ensure our newly extracted microservices don't just turn into another tangled web of dependencies, hexagonal architecture, also known as ports and adapters, created by Alistair Cockburn, really becomes non-negotiable. It is designed to completely isolate your pure business logic from your infrastructure. Why does this matter so much? Because we want to prevent technology lock-in. Upgrading a database or a UI shouldn't force a total rewrite of our core domain rules. Think of your system in two distinct zones. The inside holds your core business logic, entities, and domain rules. These have to stay completely technology agnostic. Then there's the outside, which holds your databases, APIs, UIs, and message queues. The golden rule here is absolute. The inside must never, ever have knowledge of the technical details of the outside. Your business logic simply shouldn't care if it's talking to a SQL or NoSQL database. Section 4, ports, adapters, and boundaries. Managing communication cleanly. That strict isolation raises a huge practical question. How do the inside and outside actually talk to each other without creating tight coupling all over again? Well, we use ports. These are technology-agnostic interfaces that define the conversation. Inbound or primary ports literally drive the application core. Think REST API controllers or web UIs sending commands in. Outbound or secondary ports are driven by the application, like your core asking a database repository or external APIs for information. They beautifully separate the what from the how. And that leads right into adapters. Adapters are basically your frontline translators, taking external signals and converting them to core formats. Because you can plug multiple adapters into a single port, your core logic only ever relies on abstractions. This perfectly enforces the dependency and version principle. It ensures messy SQL queries stay entirely out of your pristine domain logic. Want to swap a REST API for a GraphQL API later on? You don't even touch the core. You just write a new adapter. It's a real game changer. Finally, Section 5, Distributed Data and Sagas, tackling the data problem. Now, isolating logic is one thing, but as any senior architect will tell you, the real nightmare in a migration is the data. We have to face what the industry calls the distributed complexity tax. Unpredictable network latency, the lack of a centralized enterprise service bus, and the massive headache of maintaining data consistency. Once you smash apart a shared monolithic database so every microservice has its own store, keeping immediate, traditional transactional consistency becomes incredibly difficult. So how do we fix this without falling back into the tight coupling trap? You've got to adopt the saga pattern. This means using asynchronous messaging to manage and coordinate distributed transactions across those independent databases. You kind of have to accept eventual consistency as your new standard instead of immediate consistency. I know, it's a major mindset shift, but it is absolutely critical for system resilience. Here are your rules of engagement for data. First, decentralize all data ownership. Second, avoid synchronous API calls that create real-time dependencies. I mean, if one downstream service hangs, your entire request chain hangs. Instead, lean into lightweight, asynchronous messaging, like pub/sub or event streaming, and aggressively design for fault tolerance. This combination of decentralized data and async events is the secret sauce to preventing those dreaded latency bottlenecks. Let's wrap up with a final thought for you to take back to your engineering teams. Are your current system boundaries protecting your business logic, or are they trapping it? As you evaluate your legacy systems today, really ask yourself if your architecture is setting your teams up for long-term scalability. Transitioning from a monolith to microservices is a challenging journey, for sure, but with strategic patterns like the Strangler Fig and hexagonal architecture, it's incredibly rewarding. Thanks so much for joining me on this explainer, and keep building resilient systems.